What we see here is a representative volume element of a syntactic foam. And of course, the question that you may be interested in is how on earth did I create this type of model? Considering that it has this really interesting thin microspheres that are locked within a matrix medium, which is essentially what a syntactic foam is. If that's what you're interested in, then sit back and relax as we get into this video so I can show you how you can do this. As we get started with this, I would like to talk a little bit around the background of a syntactic foam. So what is a syntactic foam? Basically, it's a type of composite material formed by putting together hollow spheres, which are generally regarded as a microsphere. And these hollow spheres could be made from a glass, from a ceramic medium, from a polymer, or even a metal, which are then held together by some form of a polymer. So, and that becomes what a syntactic foam is. And the word syntactic essentially means put together. So the concept of a syntactic foam is microcapsules that are put together, bound together using a polymer. So this is sort of an example of what a microcapsule could look like, what a syntactic foam could look like. So essentially what you see here is these are sort of the spheres that are then bound together within a matrix medium. And so you've got this random distribution of spheres. They could be of different diameters or simple diameters. For this video, we're going to work with a monodisperse diameter. So in which case the diameters are exactly the same across the structure. So if you look into the microstructure of a syntactic foam, this is sort of what you will see. And this image is taken from Wikipedia and essentially shows you the distribution of these microspheres. And you could see some very interesting things here. So the first thing I think that is very obvious here is that some of the microspheres are actually broken. And that's something that happens when you put these things together, that the microspheres can break depending on how strong it is. So some of them are quite broken. And also during the compaction process, you will also experience some sort of breaking of this microspheres. The other thing that you notice here is that the microsphere is essentially what you see here, which is a single microsphere. And what I would intend to do here is to create a representative volume element. And in this instance, I'm going to study a representative element that's got a length of 80 and a height of 80 and a depth of 80. And within this medium, we want to then use it as a representative volume element for our micromechanical analysis. And so if you look more closely, right within here, we can see that this is a typical microsphere with a diameter of 30 microns. So this is sort of the specification that we're going to work with in this video. Now, if you look more depth wise, especially for the broken microspheres, one of the things you will notice is that the walls of these microspheres are quite thin. They are really comparatively thin compared to the diameter. So the diameter of this system is 30 microns and the wall thickness is just 1 micron, for example, in this instance. And so this is what we need to accommodate as we begin to work with our microsphere. So at the end, this is a representative volume element that we want to generate with a certain length, width, and height. And these are particularly the parameters that I want to work with. So I work with a length of 8 micron, height, width of 8 micron. That's the matrix dimension, which is the part that are a bit of bluish greenish in color. Now the next bit here is the microsphere. It's what are the dimensions? I did allude to that already. We're working with a 30 micron diameter with a thickness of 1 micron, something really very small. That's what we would have here. And of course, to create the microspheres within this matrix medium, we need to know exactly the location in space where they are randomly distributed. So randomness is essential in working with this. And secondly, these microspheres do not overlap, okay, because they are completely enclosed entities, so they don't overlap. Rather, what could happen is that they will break. So we need to know the center coordinates of each of these spheres that make up the system. So, and what I've done is that I've used a software that I've created, which is called Monte Carlo Gen 3D, which again, it becomes available for you to download. So you look in the description section of this video to see how you can get hold of that. But for this video, we are going to work with these different coordinates. So I've got coordinates for the inside particle center coordinates. So there are particles or microspheres within the system, okay? And so these are the coordinates, the x, y, and z coordinates of each particle. And the ones that are also on the edges have also indicated what the coordinates would be. The idea here is so that you have periodicity of material. So the idea is that if you want material at one corner, it will have to be replicated on the other corner. And this is really to preserve the number of microcapsules within the window. And so periodicity of material is an essential feature for this sort of things. And so this is what we have here. So I've got that coordinate as well. So we're going to combine all that, and there are about 15 microspheres that we're going to create for this single system. And the volume fraction that we're working with for this is a 20% volume fraction. So once we've created it in this format, where you still have these microcapsules right on the edges and the ones that are within inside, we don't know how to work with it in that way. We have to trim it. So there will be a trimming operation of this edge microspheres, so that at the end we get to what we are hoping to achieve, which is the idea of having a representative volume element that consists of excellent distribution of microcapsules within a matrix medium. So that's the theory of what we're going to do. If you are liking this kind of content that I'm creating, especially around syntactic foams, I really would appreciate if you can like this video, or just leave a comment in the comment section of this video to let me know what you really love in the whole presentation that I'm making. You know, what aspect of it is very exciting to you. Is anything unique that you're learning that you probably don't know before? So I really like to know about that. Please leave a comment, and it will really help me get feedback from the audience of what's going on with this. And finally, if you haven't subscribed to this channel, it really do me a world of good if you can subscribe, so that when content that I'm making like this becomes available, you'll be one of the first to see it. And you know, we continue to create a community of people who are working in the area of computational modeling and the sort of, you know, kind of simulations that I'm doing. So thank you for doing that. So let's go into Abacus as I begin to show you how to build on these models. So here we are in Abacus, and what we're going to do is to create the matrix medium first. So I'm going to call it just a matrix, and it's going to be a 3D matrix system. I'm going to use a deformable solid extrusion, these normal things, and we're going to start from the origin here. So the origin is 0, 0, and of course we want it to be 80 by 80, which is essentially the direct dimension that we're working with. And then we'll cancel this procedure and click done. So within this done, then I'm going to extrude it so that it also become 80 depth-wise. So that's very straightforward. We generate our matrix that way. Then the next thing we need to do is to create a sphere. So I'm going to call this a solid sphere. Okay, so we'll call it a solid sphere, which is a complete sphere without the microcapsule. And I'll explain that in a moment why we're doing this. So what do we do with this solid sphere? So again, it's a 3D system, deformable, solid, but we're going to use a revolution approach in a revolution type to create the structure. So that means we have to first create a side of the system. So it says here, schedule section of the solid to be revolved. So I'll use this option, which is center, create an arc. So the center is at 0, 0. This system has got a diameter of 30, so it will have a radius of 15. So what I'm going to do is I'm going to find this top end, which will be 0 and 15 at the top end, and then we need to go to the other end, and that will be 0 and minus 15 at the bottom end. And then I'll just need to close it up. So this is creating a solid microcapsule, a solid sphere initially, and we now click done. And the next thing it would ask us is we want to revolve. So we revolve it by 360 degrees so that we can get our full our full sphere. So that's number one, information of what we're going to do. But clearly we want this to be distributed into multiple places, and we have it in many places. So what are we going to do? Okay, so what we're going to do is that we're going to quickly go into the assembly module. So within this assembly module, I'm going to create instances of this sphere. So we want to create up to 15 of them because we know it's going to be 15 based on the coordinates that we have before. So I'll click 1. So if you look in here, we've got number 1. So I'll do the same thing. I'll get the second one done. So we keep going through that until we have all the 15 spheres. Okay, so we'll continue. Number 4, number 5, number 6, and we'll just do that until we get all 15. So what we have here are the 15 instances of this solid sphere. But clearly, if I also create an instance of the matrix, so what you will notice is that actually the matrix is there and everything is all sort of represented around here. So if I move this to part instances, so you can see everything is all around here. And that's not what we want. We want to distribute it into positions so that it will take the coordinates that we want before. So let's go to MATLAB right away. So within MATLAB, remember, I've taken those parameters, those coordinates, positions, and I've basically saved them inside MATLAB in this form. So I've created them and put those coordinates. So the first one we're going to look at is the inside spheres. So if you look about inside spheres, so this is sort of what we have. So these are the coordinates of the inside spheres, and this is how the structure will look when you plot it in terms of 3D space. So the thing that we're trying to create will look like this, with some of the fibers trimmed off and all that. So this is essentially what we're looking to create. And so these are the coordinate positions. So we're using these coordinate positions to translate and create the model that we want. So what I will do is that I'll copy this first entry for the inside sphere, and then go back into Abacus, and then I'm going to use the translate button. So if I click the translate, so you say which instance do you want, I'll just click that instance and click OK. So it will take one of the instance. It's located at position 0. Where do I want it to go? I'll paste what I've copied, and instantly you'll see it goes inside. So I'm going to let's probably put some transparency on this data, so you could see, okay, so there's a bit of transparency here, so we could see inside there is the fiber that's been located inside the structure. So it's been translated from here to there. So we go back to MATLAB, get the second coordinate position, Control C to copy, then come back here and say, okay, I have to click done, and then I want to translate the second instance. Click done. It's starting from the origin, and then this is the position I want, and then it goes inside there, and we click done. So we now go and do the third one. So translate this instance from where it is to where I want it to be, and then we get it into that position. Click done, and then we can do the same, get the fourth one. So translate this instance, done, enter, position this. So we're going to quickly do all that for all of them. So we've done the fourth one. Okay, so at this stage we have utilized all the inside spheres, what is defined as inside spheres, in the initial inside particles in the initial stage, which is what we see here. So what we then want to do next is to create also the edge spheres. So if I clear the screen and I'll call the edge spheres that we have, so there are 8 of them in this instance, and we need to do precisely what we've done before. So I'll copy that, and then again I'll translate an instance of this from the initial position to where we want it to be, and so you can see it's there on the edge. So we'll just do it for all the remaining points. We get to the last one. So again, we'll select that, click done from the initial position to where it is, and every one of them is all done. So if you look around the system, you can see that we've migrated all the particles into the edges where they need to be, and they are all appearing as correctly as they're supposed to be. So we're happy with what we've seen here. So what I will do is I'm just going to turn off this datum line. So if you go to view assembly display options, and in the datum, I'm going to say show no datum at all, so that I have a clean system. So you can see the whole structure looks correct, and it's ideal in the way we want it to be. Okay, so that's the first stage of this model. So what we're going to then do is I'll leave it at this stage, and I'll just rename this and call it solid model. Okay, and then I'll create a copy of that model, which I'm going to call the voided model. So I want to harvest exactly what we've done here. So in the solid model, what we're going to then do with the solid system is that we're going to use it to create a voided system. So what do we do now? So again, we go back into the assembly module. So within the assembly module, we click on this option which says merge cut. So I want to merge all the microspheres together. So I'm going to call all solid microspheres. So I want to have it as a single entity. I'll merge them, return all the intersecting boundaries, go to the instance and select from here to number 1. So I'll basically click here, Control Shift, select all of them to the end, and then click OK. So once we've done that, so you can see that there's this microspheres within the voided model. They are all represented here. So if we then go back into the assembly module, so what you will see here, all these ones are hidden. The matrix is still there. So I'm going to then extract this matrix. So if we bring in the matrix here, so these are what you see together. So I'll look at part instances, so they're still fine. So what I'm going to do now is I'm going to cut off the matrices away the microcapsules from this. So I'm going to use this option and say, okay, I want to create now the voided matrix only. Okay, so we're going to use the cut operation and we suppress the instances. So you continue. So select the instance to cut. The instance we want to cut is the matrix. Okay, and what we want to use to cut it is clearly the microcapsule solid one, and that gives us a voided matrix medium, so that the next part of this is to bring together the microcapsule in itself. So what I'm going to then do is we'll go back to the top end where we have the solid model. I can rename this solid model and just call it the syntactic foam, because that's what essentially we're going to have. So within the syntactic foam, so if you look into what we have, I'm going to then go to model and copy objects. So I'm going to copy from the voided model to the syntactic foam, and what we want to copy is the part that was created, which is the voided matrix only. So I need to bring it into this new model. So once I bring it into this new model, then this matrix will not be relevant anymore. So I could just leave it, so it wouldn't be relevant anymore. So what we still have, we're still having the solid sphere, which is not ideal. So I'm going to rename the solid sphere and call it a hollow sphere. Okay, but what do we need to do with this hollow sphere? So if we go into future solid resolve section sketch, so that's still a solid sphere. We don't want it to be this way, so we're going to do a similar thing like we did before. So we start from 0, 0, and somewhere at the top end here will be 0 and 14, and that's because we want only a 1 micron thickness, and we come to the base here with 0 and minus 14. So that's what you get here, and then we can use the trimming option to trim the line in between. So basically we've got a structure with a thickness of that, and then we click OK. So it needs to regenerate the part, so future regenerate. So if I cut it open, so you can see now we have a proper structure that is open as a microcapsule. And if we go into the assembly module, so within the assembly we can also cut it open and just cycle through to make sure that it's all open and that's perfect in the way it's supposed to be. So we have microcapsules also on the other side, and within the assembly module we look at the instances we have. So we've got all these solid spheres, which this instance probably we need to just match them. So I'm going to collect all of them and call basically microcapsule all. So I'm going to match them, suppress, return the intersecting boundary, and what we want here are all the microcapsules together. So we've got that. So they are all now one entity. This matrix medium, we don't want it because it's not voided, so we're going to suppress it, and we just need to bring in the voided matrix only that was created. So once we bring that in, and we can cycle through, and you can see essentially that we have a structure in the right way, because the matrix is voided and the microcapsules are also open inside. And so that's an excellent way to show what we have done here. So the final thing we can do is, depending on what you want to do, some people would then take this model forward and then try and apply surface contacts between the microcapsules and the matrix, or do whatever they like. But I'm going to assume that both of them are perfectly bonded and tied together. So I'm going to sort of merge both entities. So I'm going to say, okay, here, so syntactic foam. So I'll just call it my syntactic RVE. So this is what we want. We suppress, and then we contain everything. We basically select all that and click done. So now we've got an assembly of a syntactic foam, which creates a model. So if we go back all the way to the top in the syntactic foam, we could see the model that we have here, which is this. Okay, and so one of the things next we need to do is to differentiate them. So I'll just create two dummy materials. So I'll call this my epoxy. So I'm not going to put any properties for it now. And then we also have the other one, which is going to be, so in this instance we're going to work with so we can call this just a microsphere material, whatever that material is. So we'll leave that. Again, we're not going to put any property, and then we'll create the section. So epoxy section, and we'll select the epoxy, and then we'll do the same for the microsphere section, and then we'll select that. Okay, so now we have those two things. So we can go on to Syntactic Foam RVE and do a section assignment. So before we do a section assignment, we can use this option, remove selected, and I'm going to change this to spheres, cells, and select that bit and tell it to remove. So this way it removes everything, leaving behind only the microcapsule for me. and then we can only assign properties on that. Select that and then click done. So we now make it to be microcapsule only, and we can invert that so that what is left would be the original metrics there. So we select that again, and then we'll make it to be the epoxy section, and we resume and return everything. So we've got a system complete, and we can look at the material model, and it shows the right representation of what we want. So we've got the microcapsules perfectly presented, but there is a problem. The problem we have here is that we've got these edge fibers that need to be trimmed. So if we click on this and we can cycle through, so you can again see, okay, so everything looks right. So we've got empty microcapsules and we've got the metrics also, everything perfectly in order. So all we need to do now is we just have to trim out the boundary fibers. So I'll go back to the part module and now click on this extrude cut option. So I'll select that face and then select that edge. So it gives me this window which I can then specify how I want to extrude cut. So I'll start from here, stop there, and then create something much bigger to encompass everything, and then click done. So it means it's showing me, okay, I want to extrude cut all the way through, so you cut through. So that's one. And then we'll do the same thing from this other face. So I'll select that face and select that edge, and then it gives me this window again. So I start from there and go to this end and then encompass everything and click done. So it brings to this window again. I want to extrude cut all. So at times just these two extrude cutting is enough, so we can have a look and make sure that everything is fine, and it does look like it has cut off every boundary fiber perfectly as it's supposed to be. And then you could, if we look at the edge, so you could see what's happening here. If we put a bit of transparency, so you could see what's happening here, that we've got the fibers or the microcapsules internally, the ones at the edge, and everything looks perfectly all right. And that's what we want to do with this. So that's how you're going to show how to create a representative volume element for a syntactic foam. If you really love the kind of content that I'm making, please do subscribe to this channel, and do leave me a comment of what you think about the video, or maybe an idea of a video that you would like me to make, and I'll be very happy to consider it. If you want to see how you can do a compression test on this sort of material, then this is the video that you want to look at. Thank you for your interest in this channel. I'll see you in the next. Bye bye.